In this short video, I will present our group project for subject 1214 Computer Architecture.
This is our group member. We have Afiq, Akmal, Damia, Sabrina, Dayanti and Norashikin. I will present the RISC CPU simulation. For introduction, this section presents a simulation of a basic reduced instruction set computer, which is RISC CPU. The objective is to understand the fundamental operation of a RISC architecture through a Python-based simulation that mimic the fact decode execute cycle using a simplified instruction set and core CPU component. This simulation demonstrates how the CPU processes instruction, manipulates register, and memory the house execution. The objective is to simulate the fundamental operation of a RISC CPU architecture, focusing on simplified instruction execution and external CPU component behavior. This simulation helps students understand instruction cycle and performance through hand-on implementation. Next, the CPU component and function. For PC, which is program counter, this hold the address of the next instruction and automatically increments unless modified by JMP. Next is IR, which is instruction register, which the function is for temporarily store the fetch instruction for decoding. Next is general purpose register, which is used to hold data and intermediate result during execution. Next is arithmetic logic unit, which is ALU, which this is for perform add and sub operation. Next, we have main memory, 64-byte stimulate memory array to store both instruction and data. Next, I will present the instruction set design. The instruction set we use includes 6 basic instructions. This include loading and storing data, arithmetic operation like add, sub, and program control using JMP and HALT. These instructions are simple, reflecting the RISC principle to reduce complexity. Next is program implementation. In this simulation, we implement a basic program to test the RISC CPU. The program load 2 values into registers, add them using the ALU, store the result and HALT. This allows us to demonstrate the instruction cycle clearly.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abang Afiq Aiman, and for my part, I will be presenting the program execution for the RISC CPU simulation. So first we have is the program instructions. So this is a simple program that we wrote for our RISC CPU simulator. It consists of 5 instructions. First, we have is the load 2 values for memory addresses 10 and 11 into R0 and R1. Secondly, we have is the add them and store the result in R0. And after that, we store the result into memory address 12. And then finally, we halt the execution of the program. So next, we have is the initial memory setup. So here we have the table for the addresses and value. So before running the program, we initialize memory location 10 and 11 with the values of 5 and 7. These are the 2 numbers we want to add using our simulated CPU. The results will be stored in address 12. So next is we have the Python implementation. So here we have is the flow diagram. So for the program is loaded in a list in Python simulating memory. The simulator fetches the one instruction at a time, decodes it, and executes it. So after each instruction, the state of the registered and memory is updated. So this replicates a simplified version of the RISC fetch, decode, execute cycle. So lastly, for my part is we have the example output. So the output shows how the CPU state changes cycle by cycle. Here in cycle 1, we load the value the value 5 into R0. By cycle 3, we've added R0 and R1 and stored 12 in R0. The result is then later saved into memory address 12. And that is all for the RISC CPU simulation. Thank you.
I'll be presenting about the basic principles of cache memories, focusing on three key aspects, which are the types of cache, mapping techniques, and replacement policies used in cache memory design. Let's start with the types of cache, which are organized in a hierarchy. First is L1, the smallest and fastest cache. It's closest to the CPU and helps reduce the traffic to the next levels. L2 is larger but slower, and it helps reduce memory access by storing slightly less recent data. L3 is the largest and slowest, shared by all CPU cores. It plays an important role in enabling intercore communication and data sharing. This setup allows the system to access frequently used data much faster than if it accessed main memory directly. Next are mapping techniques, which determine how much data is placed into cache. Direct mapping is the most straightforward method. Each memory block maps to only one specific cache line, while set associative mapping gives a bit more flexibility. A memory block can be stored in any one of a few cache lines within a set. Fully associative mapping offers the most flexibility, allowing any memory block to be placed in any cache line. Finally, let's discuss replacement policies. These determine which cache block to replace when the cache is full. First in, first out, FIFO removes the oldest block in the cache. This is easy to implement and ideal for systems with strict limitations. Random replacement removes a block randomly. It uses the fewest resources, so it's used in systems with limited processing power. Least recently used, LRU removes the block that hasn't been accessed for the longest time. It's commonly used in hardware cache due to its efficiency. These policies help manage limited cache space while trying to keep the most useful data close to the CPU.
I will demonstrate a cache memory simulations using the three different replacement policies LRU, FIFO, and random, all under a fully associative cache mapping. So this is the example or one of our code source, which is we are using the C language to show the cache simulator. So this is the FIFO for a long pattern cache simulator. As you can see here, on the top of our code, we are using three of these to define the block size, cache size, and total cache size to calculate the rate, hit rate, and the cache capacity. So the program uses fully associative mapping, which means any memory block can be placed in any cache block. So this setup helps us test how different replacement policies behave under the same condition. So now I will run and compile the program. So I close. So this is the sample output, which is it shows that we are using the block size 16 bytes, number of cache block is 4, total cache size is 64. Here, you can see that the program show when a memory address is hit or it missed, and which is placed in. So at the end of it, you can see it displays the total access, hit rate here, and catch hit and catch miss. So in this case, the FIFO achieved hit rate of 13.33%. The execution time, which is 1.443 seconds. So next is 3.3 results under different setting. We have a short pattern for test A and long pattern for test B. So here, a table comparing the result for LRU, FIFO, and random. So if you see here, you can see the LRU performed well for the short pattern, but was slow, which is the execution time is very hard. It takes many time to execute. But for FIFO, in long pattern, it gives the best hit rate, which is 13.33% hit rate. But the execution time is slower from the other if you compare to the LRU and random. For random policies, it was the faster to run, but had a 0% hit rate in the long test. So in conclusion, the simulation show that different policies work better in different scenario, which is in this case we have short pattern scenario and long pattern scenario. So we know that LRU is good for data that reuse often, and FIFO is simple and work well in loops, while random is fast but not reliable. So that's all from me and my group.
Hi, I'm Noreshikin. Today I will demonstrate how a cache memory simulation works using the LRU replacement strategy. First, this one is for define a cache or a block size. This one, the list of memory address being accessed. And this array for stores a current data in cache, and cache index is tracks usage time. This for check for cache hit. If miss, replace block using this LRU is called, and then just a normal. This for the output. So we run the program. This output shows whether it's access a hit or a miss, and which block is used or replaced. Next, I will show how the random replacement strategy works for cache memory. First, we set the random number generator for different results. This time, use this code. We check for cache hits in this part. If we miss, we pick a random block to replace it. There, this the code. So this to show the output. Yeah, we run this program with F11 in the keyboard. Okay, this the output of the code. Every time we run this program, the replace block might be different because it's random.
Thank you for watching.